In this video, we're going to introduce the Pythagorean theorem. The Pythagorean theorem is one of the most famous theorems in mathematics. You've probably heard of it before. And in this video, we're going to investigate why it works and how it works, and in later videos, we'll apply it. So first, we're given these two diagrams. Notice they're both squares, and we're asked to find the area of both of them. So you may already see that, except for the coloring, okay, they are actually identical figures. So let's find the area. Here we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So figure A has an area of 7 times 7 equals 49 square units. Okay. And figure B, even though it's colored differently and it's partitioned differently, it also has a length of 1, 2, 3, 4, 5, 6, 7 by 1, 2, 3, 4, 5, 6, 7. So it is also 49 square units. So now that we've established that these figures have the same area, we're going to look at the different pieces, determine their areas to develop some ideas. So let's look at the next slide. Find the corresponding areas in figures A and B and fill in the table below. So for figure A, we're asked to find the area of the pink rectangle. So here's our pink rectangle, and notice it is 1, 2, 3 by 1, 2, 3, 4. So let's also add a column here. We're going to call it the number of pink rectangles, or the number of the type of figure we're looking at. So since there's two pink rectangles, both of them, to find the area, we'd multiply 3 times 4. This one is 4 times 3, which is equivalent, and our result is 12 square units. Okay. And we're going to add a total column. Now, since there's two of these pink rectangles and each one has an area of 12 square units, the total area for the pink rectangles is 24 square units. Now we have the green rectangle, okay, and notice this is actually a square. Squares are rectangles, but both sides have the same length, so it's 1, 2, 3 by 1, 2, 3. And there's just one of these, and that's 3 times 3, and I'm also going to write that as 3 squared. 2 factors of 3 is 3 squared. So that area is 9 square units, and since there's one, that's a total of 9 square units. Looking at the orange rectangle, which is a square, 1, 2, 3, 4 by 1, 2, 3, 4. So we have 4 times 4, or 4 squared units, which is 16. And finally, we're asked to find the area of the blue triangle. So notice there's 1, 2, 3, 4 blue triangles. And even though they are directed in different ways, meaning this has side length 3 here and 4 here, and this one has 3 here and 4 for this side, notice that all 4 of these rectangles are identical. And their areas are 1/2 times 4 times 3. So the area of a triangle is 1/2 the base times the height, which is 6. And since there are 4 of them, that area is 24. So now let's look at the next question. Use the information in the table to find the area of the yellow shape in figure B. So here's the yellow shape in figure B. It looks like a square, but we're not sure yet. And notice we can't measure the side lengths because it doesn't line up with the grid. Okay? So we can use this information to find this information by using the additivity principles. So notice that the pink rectangles, the sum of the pink rectangles and the sum of the blue triangles actually correspond. Okay, so we could think of, let's label this in red. We call this triangle 1, triangle 2, triangle 3, triangle 4. We can cut these rectangles in half. Okay. This half of this rectangle matches up to 1. This part of this rectangle, it matches up exactly with 4. This rectangle matches up with 3. And this rectangle matches up, or this part of the rectangle matches up with 2. Okay. So that tells us that this yellow shape is equal to the sum of these two, the green square and the orange square. Okay. So yellow shape is equal to, we'll put green plus orange. And from the table, we had the green was 3 squared, the orange was 4 squared. And that equals 9 plus 16, which equals 25. Okay. So that means the area of the yellow shape is 25. Okay. Now we're told the yellow shape is a square, but how can we tell this from figure B? Okay. Well, looking at figure B, notice that these 4 sides, okay, are what we call the hypotenuse, or the longest sides of each of these triangles. So these 4 triangles are identical. Okay, they're just moved around a little bit like we saw here. Okay, but these sides are equivalent to these diagonals in this figure, so that means they're all equal. So we can say its sides are made up of corresponding sides of identical triangles. So that means all of these side lengths are the same, and that means the yellow figure is a square. Okay. Now we're asked to find the length of the yellow square in figure B. Well, since it's a square, we know that its side length, which is the same value times itself, equals 25. Okay. So we want to find that side length. Well, notice 25 is 5 times 5, okay, which is 5 squared. So this is asking us what number multiplied by itself gives us 5 multiplied by itself. So that means our side length must equal 5. Okay? And this is the idea of a square root, which we'll look at soon in future videos. So what number times itself equals 25? That number is 5. Okay. So notice this is the basic result of the Pythagorean theorem, is that 3 squared plus 4 squared equals 5 squared. Okay, and this is in a specific example, but this square, which is 3 by 3, plus this square, which is 4 by 4, equals this square in the middle, which is 5 by 5. And we're going to extend this result to work on different problems. This is a nice example where all the numbers are integers, or whole numbers, 3, 4, and 5. It's special. It's called the Pythagorean triple. But we're going to extend this idea so we can use this to find the value of other missing sides in right triangles.